Today I'll be talking about intelligent NPCs, basically a quick crash course on game AI. First, a quick introduction of myself. My name is GJ. I'm a game developer at 9cat Studios. Here's a QR code of the slides if you want to keep them. So if there's any moment that you want to take photo of the slides, like this is the moment. Oh yeah, there will also be a recording on the Game Dev Happy Hour YouTube channel. So don't worry if you miss it. So whenever we talk about AI, there's always this very big, because it's really overhyped right now. So every time you listen about AI, you always think about ChatGPT, you always think about generative AI. But the thing is, game AI is also a part of this whole big AI space. Yeah, today I'll be talking about game AI in general, and will really not really be directly related to generative AI. What is game AI specifically, and what makes it so different from other kinds of AI? So to me, game AI is quite special because, for example, in a context of NPCs, you want them to be intelligent, but at the same time, you want some creative control over them, right? Like you want to provide a unique player experience to the players. You want to give personality to those NPCs. So you don't really want them to be that smart. You want to give them some control, but you also want some degree of unpredictability, right? You want them to do something that you won't expect. Or you wanted them to do something funny like Skyrim NPCs with an arrow to the knee. It's kind of a balance between the perfect intelligence, but you want something dumb that's also cute at the same time. So that's something special about game AI. When we talk about AI, we're normally talking about the high-level system of like decision-making. So what I'm about to talk today will be mostly related to decision-making. So there's this concept in software development of a high-level system to a low-level system. Decision-making is considered like a high-level system. So once I did the decision, for example, I want to move from point A to point B, and that decision goes down to lower-level systems like the pathfinding. Oh, okay, from point A to point B, how do I get there? Are there any obstacles? What is the fastest way to go from A to B? And after we find a path from A to B, then it can go to movement. Move how many pixels down, how many pixels right. So you can see like that the high level to the low level, it's kind of like an abstraction of how you describe how you're about to do something. So game AI is often at the highest part of that. Today I'll be talking about a few ways where we do decision making. We call them decision making frameworks, decision making architectures. And also I'll talk a little bit about lower level systems like pathfinding and dialogue, because oftentimes they're always talked together with game AI. Before I begin, I want to put out this helmet. It depends. So every single game is unique. Don't always go for the shiny new toy, shiny new tool. I might say some things that sound kind of cool, and if you were like me long ago, I would go all into it, and I realized, oh, this thing is too heavy for what I want to do, or it's not really what my game needs. So it's very important to really understand what your game needs, what experience you want to bring to your players, and then look for the tools to implement that kind of experience. Another way to say it is good to have a huge toolbox, but don't use every single toolbox that you have. Always choose simplicity over complexity. Well, at least that's something I've learned over these years. So anyway, welcome to Decision Making 101. I'm going to try to create an AI together with you guys. So hopefully I will make it easier to explain the different kinds of framework when you're creating an enemy. So let's say we have this enemy, version 1, very simple. You're pursuing a player. If you're within range, you attack the player. Like really, really dead simple. So let's talk about unstructured AI, like the most basic kind of decision-making framework. Unstructured AI is basically just doing it, just writing scripts and hoping it will work, hoping it will look smart. I drew this myself. I'm pretty proud of it. So let's try to make a basic AI with unstructured AI. So basically we write two scripts. One is a movement script. Every frame you move towards the player. That's it. The second script. Every frame you check if there's a player within range. If so, attack. Like very simple. And this will definitely work for this AI. So let's make it smarter. Let's see how this framework works. Let's add a stun state. So if it's stunned by the player, no matter what it's doing, stop moving, stop attacking. Like very basic, really typical AI behavior. So let's see how we do it. We add a third script called the stun script. Let's say if the AI received damage, there'll be a flag called is stunned. It'll become true. And after a certain duration, it will become false. So now that we have this Boolean, we can put it into different scripts. So for the movement, if I am stunned, do nothing. If not, keep moving to the player. The attack script, same. If I'm stunned, do nothing. Else, I will check if the player's in range. If so, attack. Everyone's with me so far? Like, it's all good? Okay, good. So let's make it a bit harder. So let's say it can wander. If there's no player nearby, wander. If there's a player nearby, or at least you can see it, start pursuing the player. And if it's within range, attack. If it's stunned, stop. We're getting more complex, but it's still quite typical as an AI. So let's try to do with unstructured AI. Let's try to add a wander script. So if there's a player nearby in proximity, is wandering is true. If not, false. Same with stunned. Whenever you move and before you attack, you always check if you're stunned or if you're wandering. If you are, don't attack or just wander. As you can see, it's starting to get kind of messy, right? Like while I was preparing this PowerPoint, it's kind of hard to clearly show this mess. If you get what I mean. So you kind of get into this dependency hell, we call it. We call it a dependency hell. So every single script, for example, the movement script, it cannot exist without the wander script or the stun script. Or the attack, it cannot exist without wander or without stun. So while you're making this AI at first, it works. It doesn't really seem like a problem. But once you try to make different types of AI and you want to reuse scripts, let's say you want to create an AI which doesn't need to wander, but it can attack. But the attack script needs the wander script. So you're forced to add a wander script to an AI that does not need to wander. So there's this huge dependency thing. And the AI is not even that complex, right? It's just pursuing, it's just being stunned, it's just attacking. But we're already into this complexity. So that's why there's so many kinds of decision-making frameworks and architectures that arise to help us formulate these kind of behaviors. Because it's really not that complex when you're talking about it, but it becomes complex when you write it. So we enter one of the most popular framework state machines. So a state machine, if you're using Unity, you would know about it already when you're using the animator. Here's a very quick intro to what is a finite state machine. So a finite state machine, as the name says, there's states, right? So let's say here's a lamp. So a lamp could have two states, an on state and an off state. Other than states, you have transitions between states. So you can get from the off state to the on state. And how do these transitions happen? We have events. So let's say I switch up the switch. That's an event. So I will transition from the off state to the on state. So the light bulb switches on. And I switch off the bulb. And it goes from an on state to an off state. So that's like state machine in a nutshell, right? Is everyone with me so far? I hope I'm not going too fast. So when you go into or out of a state, you could do some actions. So just the state machine itself, you're just describing what state it could be in, but there's nothing about how the light actually gets on, right? You're just describing what it could be in. So therefore, when you get into or out of a state, you're allowed to do things. So like when I get into the off state, I would physically remove the light from the lamp. And when I get into an on state, I would physically light up the lamp. So that's the connection between the state, that abstraction, and the actual what is going on with the lamp. Yeah, why am I talking about a lamp? That's making it so complicated. Don't ask why. Programmers do this all the time. So okay, let's go back to our enemy. Let's try to model this with a state machine and see how it goes. We're just going to add 4 states. We have a wander state, pursue state, an attack state, and a stun state. So what's interesting about a state machine is that you cannot be in more than one state at a time. You're only at one state at every time. Like a lamp, you cannot be on and off at the same time. For this particular AI, we cannot be attacking and stunned at the same time. So here we can implement, in the middle of an attack, if someone attacked me, I immediately put myself to the stun state, and I'll stop attacking. Or while I'm pursuing and while I'm wandering, if I get hit, immediately go to the stun state. So that's how we implement this kind of AI. What's different about this AI than the unstructured AI is that you can see the attack and the pursue state, they're all separate. So this AI, it's a bit different than the previous one. The previous one, it would move while attacking because the 2 scripts are running at the same time. For this one once there's this player in range, it actually stops, then attack, then continue pursuing. Here are just like different actions that we can do when we enter or exit a state. But the details aren't important. The important part is you can see there's lines between each state. So now we're no longer in that dependency hell. Every state is completely independent of each other. And we are now free to mix and match and try different transitions and see if that AI behaves more like how we want to. And we could always choose only like, let's say, 2 of these states together, and we can already create a new AI reusing things that we already have without writing anything new. So that's finite state machines. So finite state machines is very popular, but there aren't many popular tools for actually making state machines in popular game engines like Unity, Unreal, and Godot. Because state machines, at least in a programming perspective, they're often described as not that hard. Again, not that hard to write, but it's actually hard to maintain and hard to debug. Like, if something wrong happened, it's hard to know what's going on with your own code, actually. At least there's an official Unity tutorial teaching you how to write finite state machines. And I highly recommend this book called The Game Programming Patterns if you're a programmer. Highly recommended book, mentioned in a lot of different places. And they have a whole chapter on state. So basically, if you know the whole concept of state, no matter what game engine or programming language you are, you could always implement finite state machines. But anyways, let's try to make the enemy more complicated. So other than wandering, stunning, let's add one more attack pattern. We add a ranged attack. So other than melee, when you're close, you can also, like, say, use a bow when you're far away. Let's go back to the very beginning, unstructured AI, how it will look like. Basically, we just expand upon the attack script, testing your range, first seeing if you're far away or if you're near, and attack accordingly to whatever range you are in. For a finite state machine, the attack at the bottom would split into 2 states. And there's a problem that you start to see with finite state machines and why it's not that popular in AI. We call this state explosion. The more states you add, the more transitions you have. So we call this an ON squared complexity. In easier terms, it's like if you add 2 states, you have 4 more transitions. Add 3 states, you have 9 transitions. 4 states, 16 transitions. So it gets really complex really fast. And this AI is not that complicated, actually. People try to think of other ways, other than state machines. How do you structure an AI? One possible improvement upon the state machine is having an any state. So you see that upper any state on the upper right. So no matter what state you are in, if a player attacks you, get into that stun state no matter what. So that sort of makes it better slightly, but it's still not optimal. So, and there's also quite some other problems with this. So like, what if you are in melee range and the ranged range at the same time? So which attack does it choose? Like, just by looking at this state machine, you can't tell which one has higher priority. Like, there's no sense of priority in a state machine. Or what if I want to be in 2 states at the same time? What if I want to be pursuing a player while attacking? Like, why is that not possible? Entering behavior trees. Behavior trees are a very popular AI framework. It's popularized in Halo 2 after this talk from GDC 2002. Yeah, it looks complicated, but I hope you could get through with this with me. It's basically a glorified state machine, but in a more scalable way. Behavior trees are more like programming languages, actually. So you have an entry from the top, go to a repeater. So a behavior tree, you go from top to bottom and left to right. So from the entry, you go to a repeater, which means everything, whatever happens at the bottom, we just keep repeating them at the bottom. Then from the repeater, you go to a selector, which is kind of like an OR in programming. So you either go to the left or the right. So let's say we go to the left first, right? And we get to a sequencer. It's more of like an AND node. So anything under the AND, it gets run sequentially from left to right. From entry, repeater, selector, we go to the left, sequencer, and then we go to the left again. If A, then do B or do C. So you can see that if statement, we call that a conditional. It could either be true or false. So let's say it's true. If A is true, then we can do B and do C. But if A is false, then it goes back up to the sequencer, back up to the selector, then it goes to the right, and see if it could do the thing on the right. If D, then do E and F in parallel. Behavior tree, it's really like a glorified if-else programming tree. So you're just doing if-else statements everywhere. And that's how you basically describe your whole AI. We just use different components to describe our if-else. And we'll go back to that AI example and you'll see what I mean. So I omitted the entry on the top. So we go to a repeater, then a selector. Then we go from left to right. We first check if we are stunned. If so, then we idle ourselves, right? We don't move. But if it's not stunned, we check if we're in melee range. If so, attack. If not, if it's in range, we do a range attack. If not, we pursue. If not, we wander. Like once you get used to explaining AI in this way, it's actually very simple to read and to see. It's basically a priority from left to right. Anything that happens on the left must happen first. And in behavior trees, there is something called aborting. So like if you're in the middle of a range attack and it checks that you're stunned, it could immediately go to the left side. So behavior trees are very popular for this reason because it's really simple to explain a behavior in if-else statements. So because it's so popular, there are many tools available for it. For Unity, there are 2 paid tools for it. I personally used Behavior Designer before. It's pretty good, pretty powerful. Arbor 3, I've never used it before, but there are also several open source options you may try to use. For Unreal, it is the built-in AI solution. Actually, Behavior Designer was based on the Unreal AI solution, so it's good to use. And Godot, there's also several open source solutions if you want to try out behavior trees. The other competitor to behavior trees is goal-oriented action planning. I'm just going to be throwing out these big words to you. I hope it doesn't get over your head too much. Goal-oriented action planning, or GOAP, it's developed for Fear in 2004. It's also used in Middle-earth Shadow of Mordor. The team for Shadow of Mordor have also talked about this in GDC 2015. So basically, it's kind of the opposite of behavior trees, right? So behavior trees is like this glorified if-else statement. You're explaining every single step from the beginning, how you're going to do your action. GOAPs, on the other hand, are a very different way of thinking of AIs. They start from the goal, from what you want to achieve, then go backwards from the goal. So if behavior trees, they're of a bottom-up approach from what you have, slowly building up to your actions. GOAPs are more of a top-down approach. You figure out your goal first, then figure out the actions, how to get there. And another special thing about GOAPs is that the actions to reach that goal is actually generated by the program itself. So you just define what actions an AI can do, and it will basically just build up its own plan for you and achieve your goal for you. So how does this system actually work? So let's say we can define 2 goals, 1 and 2, and we have like 4 actions, A, B, C, D. And these actions may have dependencies on each other. Like you have to complete action C before you can complete action B. And you have to complete action B before you can complete action A. So we can add into these dependencies into the actions. So let's say I want to reach goal 1. What's the quickest action I could do to reach goal 1? And it will be goal C. Okay, but I'm not yet at that state. How do I get to action C? Oh, I have to do action A first and then action B. So the program actually, based on your current state, creates its own action plan to reach your goal. So that's why it's called a goal-oriented action planning. So it's, as the name says, build plans from actions to meet your goal. Back to our AI example, let's say we give 2 goals to this AI. We give it a kill player goal and we give it a wander goal. Goals can have priorities. So let's say we only give it the kill player goal if the player is in proximity. Like if there's no player around, the goal would be to wander. Okay, so let's say we wanted to kill the player. How do we kill the player? We can give it several actions. We can give it a wander action, which just basically wanders around. A pursue action, which gets near the player. A melee attack and a range attack. What are the dependencies between these actions? In order to melee attack, you have to be near the player. In order to do range attack, you have to be within a certain distance to the player. So therefore, these attacks depend on pursue, because pursue is the only action which can get you close to the player. And there's nothing that the pursue depends on, because you can pursue anytime. So let's say we want to kill the player and we're far from the player. Then the planner, it would automatically construct a plan which is, hey, I need to kill the player, so I need to do melee attack. But before I do melee attack, I would need to pursue. And that's the whole action plan to kill the player. So that's GOAP. Gope is also popular, but I cannot find any paid assets on Unity. There's an official Unity tutorial teaching you how to write your own one, but writing your own is difficult. I mean, it's not very difficult to write. Like, you can make it work, but after you make it work, how do you analyze it? What happens if something goes wrong? Like that's a difficult part, right? So there's an open source solution. I haven't tried it, but it seems okay on YouTube. For Unreal, there's a paid asset you might try out. For Godot, I can't really find any, but you could always write your own, I guess. Other than Gopes, there are also other two planners. We call this group of AI planners. One of them is called Simple Hierarchical Order Planner, SHOP, or another one is HTN. I didn't do much research on it, but the idea is basically the same. Give it a goal, and it'll generate its own path to the goal. So behavior trees and Gopes, they're basically two of the most popular frameworks for designing game AI, at least complex ones. What are the difference? Like, when do you use which? Basically, like I said before, the biggest difference between these two is that behavior trees, you specify every single case, every single possibility in that tree, if what, do what. For Gopes, we specify goals and actions, and it builds itself. So typically, you would use Gopes if you want smarter AI, but as I mentioned in the beginning, you might not want smarter AI. You might want that control, or you don't want that unpredictability sometimes. You can also use Gopes if there are way too many possible things you can do in that map, especially in games where user creates their own maps, like let's say Minecraft. There's like way too many things you could do, so Gopes might work for that. That's what Gopes are usually meant for. But if not, if you don't need that, basically behavior tree works for 80% of games. That's why there's way more assets and way more tutorials on behavior trees, because it just works for most of the time. But yeah, you can read this article if you like. It's like just a 2-minute read, really insightful. Yeah, so that's basically the different decision-making frameworks I've come to. And here's some tips I would give if you're planning to make an AI. Any single action is definitely more complicated than you think. Like I'm just saying attack or melee attack or range attack, but there's so much going on just an attack. Like you have to show an animation to the player to tell the player, hey, I'm about to attack you. You should dodge. Like there is an anticipation, right? And when you attack, it's not just a single event. There's an animation time, like the whole slash of the sword. There's a time there. And what if you're in the middle of that slash? How do you handle like canceling that attack? Like what if it gets hit in the middle of an attack? How do you recover from that? How does your behavior tree or Gope or whatever AI system you do, how do you recover from that? So that's quite difficult. So you really have to think it through. But just like the high level system and lower level system discussion from the beginning, we normally, as much as possible, try to make the behavior tree or Gope as simple as possible. Like in the state machines I showed you a while ago, I don't show anything about anticipation time. I don't show anything about animation. As much as possible, you want to try to hide these little details somewhere else. Simplicity always wins over complexity. Speaking on simplicity over complexity, sometimes unstructured AI, they actually work pretty well. Like let's say Vampire Survivors, right? Like it's just getting near you, if near, attack. Unstructured AI works perfectly for that. Especially if you're thinking about performance, or if there's like hundreds or thousands of AI at the same time. Basically, you don't have to go for behavior trees or Gopes every single time. Yeah, that's something you have to think about. And also plan ahead when you're designing these AIs, because at least there's one special case, especially when I was working on the game in 9cat Studio. Suddenly, one of our enemies, we want them to be friendly. Like suddenly we wanted to turn it from a hostile faction to a friendly faction. When we first did that, we realized the behavior tree can't be reused at all for a friendly NPC. So if you had that in mind from the beginning, it's good to have that in mind as you design your behavior trees or Gope. And especially with friendly NPCs, there's actually quite a lot of things you have to think about that's different from enemies. So for friendly NPCs, you have to think about whether you want the friendly NPCs to be dependent on a player, like a support character. Like let's say Minecraft dogs, they would follow you and help you. Or are they like independent, like let's say Halo or Call of Duty? They would act on their own and the player is expected to follow them. There's very different ways of designing the AI based on what you want it to do. I wonder if you guys watch Pirate Software on YouTube or Twitch. Like there's one advice he gives often, which is always think of your GDD first, your game design document. Always have your game design document first. Have the overall picture of your game pinned down. Then from that, you can always think about what's the best tool or what's the best way to approach your game. Of course, the game design document could change all the time, and it should change. As you make your game, you'll find out what's more fun and you'll change it. But it's always good to have a big bird's eye view before making anything. But then again, it depends. It depends on your game, it depends on your time, it depends on what you could do. And don't think too much, just do it if ever you can't really come up with a decision. So that's decision making. And I'm going to move on to pathfinding. So pathfinding is basically a very like a mid-low level system teaching you how to move from A to B. Depending on different pathfinding techniques, you may or may not include obstacle avoidance, like, oh, there's an obstacle between me and that point. How do I get over it? Or it may or may not consider whether that's the fastest path there. There's a few approaches. One of them is called the physics approach. Physics approach is very simple. Basically, you just go towards that point, right? So if I want to get to here and I'm here, I just add a force and push myself towards that point. Like, very simple pathfinding. But this simple approach has some problems once they start to have obstacles in between. So another way you could improve this physics approach is first, using physics, I shoot a ray between me and my target and see if there's any obstacles. If so, don't pursue. If not, then go on. Or you can also improve the algorithm much more. You could always watch this guy on YouTube. I like his videos a lot. And he shows different techniques of building different simple pathfinding techniques. So there's a lot of pros of this physics approach. Like, it's really simple. Like, just, I don't even have to put much words on screen. Like, the photos is really, really sufficient to show what's going on. And it worked great for a large number of enemies. So if you're making something like Survivor type games, it's great because it's simple. But the cons, of course, are the limited intelligence. So if there's way too many obstacles, or it's a maze, it can't find you at all. Or it never really chooses the shortest path. It just goes towards you. But all of these kind of limitations could always be compensated by game design. Like, oh, maybe in game design, I don't need that many obstacles on the map. Then actually that could compensate already. But let's say you do want obstacles. Then we have the algorithmic approach. So there are several algorithms, pathfinding algorithms, to look for the shortest path to a target given the obstacles. So a very popular one is A*. This is just a really simple graphic illustration of how the algorithm finds its target. But all you need to know is that it goes through obstacles and finds the shortest path to its goal. And other than A*, there's also flow fields, which this is very popular for RTS games, real-time strategy games. So like if you a point in the map, then all of the units, like hundreds of units, will follow and go into that point. So basically, most of those games use flow field pathfinding. And the pros is that it's more intelligent. Of course, it could go through obstacles. It goes to you really quickly. But the cons is that it's really complex. And performance-wise, it's difficult, especially if the target is moving. Like, the player always moves, right? So for every frame the player moves, let's say you have 10 enemies. All of these 10 enemies need to recalculate the shortest path to that player 60 times a second. So the more enemies you have, the more of these calculations you're going to have. And it gets really heavy. And also, it's really hard to customize exactly how the enemy is moving. So let's say you want to, like, one of the enemies we implemented in our game was a hopping kind of enemy. And we used A*, and it's really difficult because when you hop, you're actually expected to move, stop, move, and stop. And it's not easy to do that with A*, especially A* with a lot of different tools you may use. They don't assume hopping. They assume just linear movement towards the goal. So that's something you have to think about. But speaking of tools, there are some popular tools. For Unity, Unreal, and Godot, they all have built-in pathfinding systems. Unity calls them nav meshes, and Unreal and Godot, they call them navigation systems. I think under the hood, they basically use A* as their algorithm. So you could go ahead and use that. But for Unity, I highly suggest the A* pathfinding project. I find this to be much more useful, and you could support way more enemies than the original Unity nav mesh. That's something for you guys to look into if you want to. And some tips. Again, do you need that intelligence? Like, you always have to ask yourself when you're making a game and you see new and shiny tools, do you really need it? Do you absolutely need it? Like, what is your aim? Is your aim just, if you just want the feeling of being chased, then you can actually do that with a dumber AI, right? But if you're not sure, I suggest you to improve step by step. Go from the simple ones, then slowly getting more complex as you need it. And don't be afraid to try out different solutions. Don't tell yourself, hey, I spent a whole month on this system, and it's not working, don't be afraid to give that up and try something else. It's basically a sunk cost fallacy. Like, the time's already spent anyway, so why not you do something better? But also, if you're a programmer, it means that you have to write flexible code to begin with. Give yourself that chance to do it again without destroying your entire game. So after pathfinding, dialogues are also quite popular in NPCs. There are a few types of dialogues. We have barks, which is like just basically this little pop-up on the head. We have subtitles, which, the guy just talks for a really long time and you can hear it or see the subtitles at the bottom. Or there's like close-ups, like Hades, like you talk to a guy and you have options. And for dialogue, there's this dialogue system for Unity, which I used before. It's quite useful, but make sure your game fits within the framework of that tool. Like, sometimes their tool is designed for a particular type of game, but your type of game doesn't really fit that framework. So don't use it just because you heard of it. And dialogue is very difficult in general, not just because of AI, but because it depends on so many things. So let's say you're playing Skyrim and you're in the middle of a quest. So depending on what quest you're doing, that AI may give different dialogues. Or depending on what inventory you have, or what you have done, or who you have killed, or what is our surroundings, or what's your health, that also affects dialogue a lot. So it's quite complicated, and it's really good to have it planned beforehand. Some tips when you're making dialogues: think about localization early. Localization, like how do you translate it into different languages? It's important to think about early because, especially if your game has a lot of dialogue, there's a lot of translation you have to do. And you have to find people who actually know the language to verify that the translation is correct. And you have to set up those localization systems in place early on, or else you'll be hard coding your English subtitles everywhere, and then you realize, oh, I need to translate to Chinese. I need to replace every single instance of the dialogue everywhere in your game, and that's a headache. So it's good to think about it early. Another thing you have to think about is dynamic variables. Like, in your dialogue, does your dialogue want to pop up, let's say, your player's name? Like, in Pokemon, you can name your character like someone stupid. Someone stupid caught Pikachu. Like, you want those dynamic variables. So that's something to think about. Text effects are also an important thing about. And how do you organize all your dialogue, especially if many characters? That's something to think about. And some honorable mentions that didn't make it to the top. Factions and relationships, they're also very popular when you're talking about AI. It's good to think about in the beginning of your game. Again, have your game design document, know what you need, then get the tools to create what you need. That's basically the end. I hope it's somehow informative.